Bonaventure is a MS student in data engineering at Jacobs University, Germany, and a research intern at Mila in Quebec. And he's working on NLP for African languages and specifically for Fon, which is a language that he's closely associated with through his family or connections. He can probably talk about that more. And David is a doctoral student in computer science at Saarland University in Saarbrücken, Germany. His current research focuses on security and privacy of users' information and dialogue systems and online social interactions. But originally from Nigeria, he's also actively involved in the development of natural language processing datasets and tools for low resource languages, with a special focus on African languages. And they're going to give two different presentations about their individual work, but also as members of the Masakhane community, they can answer more general questions about NLP in Africa, how the community formed, and other things like that.
Okay, so once again, thank you, Mr. Graham, for having us here. I will be representing, I and Mr. David will be representing the Masakhane community. I am a master's student in data engineering from Jacobs University in Bremen, Germany. And the work I will be presenting has been done with my co-worker, Chris, who is a student in mathematics and data science at the Technical University of Munich. I will be talking about our last paper, Okube end-to-end speech recognition from Fon and Igbo. So Okube is the concatenation of two words from two different backgrounds, Igbo and Fon. Oku, that means speech in Igbo, and Be, that means language in Fon. And the idea is to empower African languages, which are most tonal, mostly spoken, and try to bring them together and build AI technologies for them. So, to our idea and motivation, we found a very beautiful quote from the respected Nelson Mandela, who says that when we talk to someone or to a group of people in the language, in just a language, another language, they understand it and it goes straight to the heart. But then when we speak to them straightly to in the mother tongue, native language, it goes to their heart. And I also have such a dictum in my native language, which says that what is meaningful, what is important to us, we only know how to express it the best way in our native language. So this comes with many problems, because for those languages who represent, I think, 31% of the languages, spoken languages of the world, we have very little research about them. And like I said, they are mostly tonal. So we want to fill that gap, and we want to make sure that we create automatic speech recognition system for them that could help and ease the communication between our communities, and to make sure that also those languages are not left behind, because they are actually subject to extinction. And we want to make sure that AI and its potential is used for the benefit of all languages. So in our paper, we are not linguistic students, but we tried to go to the roots and dig deep. We provided very detailed linguistic analysis of Fon and Igbo. We also created two different end-to-end deep neural network models, one for Fon and one for Igbo. The one for Fon has achieved a state of art, because before there was only one work, and our model has outperformed that work. And for Igbo, we can take the model and the result analysis and everything about it as a benchmark for further works. So like it's shown on this table, those two languages are Africans, most likely centered in the west parts of Africa. Igbo is spoken by 20 millions and Fon is spoken only by 2 millions. we can see that those languages belong upper to the same family, but then going down to the tree, they just split a little bit away. So Fon is considered as a Bay language, which is a group of isolating language, and Igbo belongs to Igboid, which is considered as an agglutinative language. So all of them are tonals. So in Fon we have, for instance, 3 different tones: high, low, and downstep. And in Igbo we have 4. Another important, interesting aspect of Igbo is what they call code switching. So people speaking Igbo, the normal Igbo, tend easily to switch to English. So I can be, one can be speaking Igbo and then just like for a second or for 2 seconds, then put words, English words out, something like that. And it's very interesting. And we tried also to give the different kind of code switching and how often they happen and all the properties about them on our paper. So to do this work, what we've done is look for corpora, of course, speech to text data set. So for Fon, for my language, we gathered about 10 hours of speech. And the website from which the sentences have been scripted has been put in there, and the dataset is publicly available. For Igbo, on the contrary, the data was not open source, so my colleague Chris has to pay it. Then it came out that when we got the data, the transcription, because it's a transcription task, the alphabet of the alphabet was mainly English alphabet, stripped off the diacritics. And we underwent also through cleaning and filtering, because we noticed that many of samples were very noisy, and in the majority of them, they were very unbalanced on the sampling rate level, and also on the, let me say, and the clarity. So I think we had up to 207 hours of recording, but finally we ended up just using 2 hours and a half, because that was basically the small range that after listening to some sample, we thought it would be much more better and efficient to train the model with. So yeah. So then we now go to the preprocessing part, where we basically applied the most known techniques for this, which is the fast rate transformation to move the speech sample from the time domain to the frequency domain. And then, since we're trying to use something that a model architecture that was incorporating convolutional networks, so we moved those speech now into a narrow band spectrogram. I mean, we converted them into a narrow band spectrogram that is basically a 3D image that displays the energy, frequency, and the variation over the time. For the diacritics, for the text processing, based on our previous work and also the works of few other researchers, we have shown that it's important for us to keep the diacritics. So this unfortunately has not been able to be done in Igbo, since everything came without the diacritics. But we can see, if I take the example of Fon, that we have the word to, which means ear, to, which means see, and to, which means country. There's another one that is called to, which means father. So if we strip off those diacritics, we come back to the only and single word to, which is completely ambiguous. Like, we lost all the different possible contexts that we could have, and this actually could also lead to mistranslation, or also confuse the model or somehow. So we made sure that we had those diacritics by using the NFC normalization form of canonical composition. Yes. So on the model part, we tried different kind of architectures. The main component are the residual convolutional networks that are made with we applied some paddings, I think, yes. So we had some kernel of size tree We also apply the padding, which was the kernel size divided by 2 and taking the integer part, so it means 1. And then we also apply some strides. Prior to the input of the convolutional, the resnets, resconvnets have been normalized before going further. So we also use bidirectional RNNs, BGRUs and BRSTMs, and we at the end try to incorporate the additive the bidirectional attention mechanism that have shown great success and everything in the field of NLP or machine translation, to be much more precise. So here is a little bit a bigger picture of the model. So we can see that we have the mesh spectrogram, the narrow band spectrogram at the input. We normalize the feature, and then we feed them into the convolutional neural networks blocks, the ResNet, residual convolutional neural net blocks. Then goes now the decoders part. So we have a block of BiLSTM that just take the inputs, the output, sorry, from the CNN block, and the next block is the BiGRU block that takes the output from the BiLSTM block and try to do some magic. Now, in there, here in this setting, we are using the CTC lost. So we are just, since we tried to incorporate the attention mechanism, we didn't just use the attention loss, we use a kind of hybrid system of the CTC and the attention. That somehow was made to force actually the decoder, the BiGRU block, each layer of the BiGRU block to make monotonic alignment and then to improve the transcription quality. We gave a much more detailed step about how everything has been done in the original version of the paper. So as a result, for fun, we can see that, for both languages, we can see that we achieve best results, including using the attention mechanism. And we have a baseline that has been introduced and presented in 2016 by Laleye, a professor of mine, and our system has outperformed his own. For Igbo, we didn't have, that's why I was saying in the earlier that it can be considered highly as a benchmark for future works. Now, here we have some predictions about the font ASR model, and we can see mainly here that in computing the word error rate, we have what we call insertion, substitutions, deletion. Yeah, so we can see that those phenomena happen most on the decoding, prediction part, where, for instance, Akpon, we're expecting like an AA, but then on the other part of the decoding part, the model part, we got a double A. So like an A has been inserted. This also could have affected the character level word error rate, and then also the word error rate. We have also ghosting, which was supposed to be two separated words, but then the white space has been deleted by the model somehow. Now, if we go down, we can see that we on the target we're expecting the E, but then the model predicted the E will be absent. So those kind of actually insertion substitutions that are mainly trying to influence the result that we presented earlier. Otherwise, there are no major problem, major issue. And as a native speaker, those errors are not really noticeable in the speaking. It's most likely when we write them down, we can see something is wrong here. So we made available the code source for both models on our respective GitHubs. Now, we actually went further and then asked ourselves why we can see, for instance, for the gap between the word error rate and the character error rate is very huge, but then for Igbo it isn't. So we tried to give a very simple and basic explanation to that. That was the Igbo data set came without those diacritics. So for instance, in this case, for instance, where we were expecting the E and then have predicted the E with the accent, you know, the model would definitely not have been able to make those difference because we didn't really specify it. In font, we added the Latin alphabet and then we added all the possible different diacritics, letters with accent. This definitely helped the model and everything. And we can also see for further examples how not putting those diacritics in could have influenced the results. So I am at the end. So in my name, in my language, we say Enochenumi to say thank you. No, actually there are no really words that means thank you. It's just a way to express gratitude. And from Igbo, if I can try, is pronounced Dalu. So I thank you for your attention. And if you have any question, I'm free to answer to them. And I will hand over to David. Thank you.
Okay, so I'm talking on something completely different. So I'll start with the Masakhane NER project, which we call MasakhaNER, named entity recognition for African languages. And at the end, I will probably just talk a bit about my own research on privacy. So I'm a student of Saarland University, and I work also with Masakhane to encourage the participation of Africans on working on African languages. So this work was a collaborative work by a lot of people. So I'm also happy that people from CMU also participate, like Graham and Shruti. So we did this in the span of like around 6 months because we had volunteers from different countries, and they helped to create this data set. So the main motivation, one of the main motivation is to increase participation of Africans in NLP. This is one of the goals of Masakhane. So for example, if you consider the NLP conferences in 2018, most papers from all over the world except Africa. And how do we increase this participation? How can we help Africans maybe trying to help them to increase the knowledge in NLP and so that they can work on African languages, and also to encourage benchmarking of NLP models on African languages. And the reason is because most 30% of the world languages are actually African languages. And these languages are not spoken by few people. On the right-hand side, you can see that apart from having most of the languages of the world, like 30% are African languages, when you consider the average number of speakers per language, you find that apart from European languages, African languages are the next, spoken by thousands of people per language on average. And so our contributions are the following. First, we create like human labeled NER data set for about 10 African languages. And we also make them publicly available because there are some data sets that already exist that either are not human labeled or are not publicly available. And we also want this data set to come from local sources. And of course, we train popular NER models. And we also explore how to improve the baseline models through gazetteers and transfer learning. And we also release code and data and model. So some of the previously annotated NER data of African languages, one is the WikiANN. This is automatically annotated from Wikipedia by considering the links to Wikipedia entities. And we have the Sadila data set from South Africa covering all the South African official languages. This is based on government data. And also we have the Lurali data set, but this is not publicly available. I think through LDC, one might be able to get this data set. But the problem is that it's not even available to most Africans that who try to evaluate or work on this kind of data set. And so we also have some small corpus for less than 2,000 sentences for Hausa and Yoruba last year. So we focus on like 10 African languages, and these are the choice of our language is because we have annotators for these languages that are in Masakhane community, and also number two, because we have available text corpora. For example, we are targeting the news domain, so we have news articles for these languages. Most importantly, because actually these languages are also spoken widely in Africa. So if you take Swahili, for example, in the East Africa is like spoken by many countries in East Africa. And I was surprised that we don't have like Cuban label, like NER dataset for Swahili prior to this project. And also this language is spoken by millions of speakers, and we have many of them in East Africa, and we also have West African languages like Hausa, Igbo, Yoruba, Wolof, and Nigerian Pidgin. So Nigerian Pidgin is an English Creole, spoken mainly in Nigeria. So we annotated for these languages. So there are interesting characteristics of these languages that you might want to pay attention while building NER models. For example, if you have a sentence in English, the Emir of Kano, Toban Zang, who has spent 18 years in Nigeria. So if you translate this to Amharic, you find out that the first thing is that the script is different. So if you want to do transfer learning from English to Amharic, then this is difficult because of the script. And also, I think it's also lowercase in their language, which is not very obvious here. But if you consider all the languages that use the Latin characters, many of them preserves a lot of things, properties, entities from English. Like Zang is almost the same. It's like the same throughout all the languages except for Amharic. And Kano is also almost the same with the location. And except for Wolof and Yoruba that uses diacritics. 18 years is translated, the years is translated, but some languages, they actually write out 18 in their language, like Yoruba. We, instead of using 1/8, we will use like Odun Meji Dilogun. And Nigeria is also translated in different languages. So for the annotation, we consider annotating for 4 named entities: personal name, organization, location, and date. So we combine any date and time, and we just like annotate all of them as date. So we use a tool called Elisa, first through the help program, and they connected us to Hengif and I think Yinling at UIUC. So they provided us with the Elisa tool that they made freely available to us to use for annotation. The tool also provides like entity level inter-agreement score. So it allows like annotators to discuss what they have done at the end of annotation so they could improve their inter-agreement score. And this really helped us to have high quality final data set. So the annotators, again, they are mostly native speakers from Masakhane who are interested in NLP. And we had like minimum of 2 annotators per sentence in each of the languages. And this kind of took like 6 months. And because they are volunteers and they just do it in their free time, of course, we had more annotation going on around December while we are preparing for the African NLP workshop. So looking at the inter-agreement score, if you just look at the scores from the Elisa tool, we have something around 0.96 and 1. But when we like take more, we consider like the Kappa score, it's also very similar. and we find out that all the languages with 1.0 is just because we gave them an instruction that you're just two annotators and you should try to resolve all the disagreements. So basically they just have a phone call or a Zoom call just to resolve the disagreements. That's why we have like perfect score for that. And the other languages that have more than 2 annotators, we did majority voting just to select the annotators that is commonly agreed on by annotators. The entity that was commonly agreed on by annotators. So our final data set is this, and most of the sources coming from news articles like BBC, Voice of America, or some other local newspapers that are popular in some of the countries that this language is spoken. So most of the data set is actually around between 2,000 and 3,000 sentences, except for Luo, which is very low resourced, and we had like less than 1,000 sentences for this. And also Wolof, which when you consider the percentage of entities in the data set, they're very small. So we want to see how, if we can benefit from transfer learning and other techniques to improve the performance for Luo and Wolof, for example. So for the NER baseline models, we use like common popular models like CNN by LSTM, CRF model. This is very popular prior to the BERT-based model. Then we have another model called MinE by LSTM. We just call out this word. And the idea is that we still use by LSTM model, but we don't have word embeddings for these languages. For the CNN by LSTM CRF model, we just randomly initialize this model. But for the MinE, what we did was to extract sentence embeddings from the BERT-based language models, and we average the output embeddings from the 12th layer of the language model, and so this gives better performance than if we consider the first token of the output layer of the BERT model. This is the CLS token. This is the first token. And this token is what is used to fine-tune like BERT-based models end-to-end. So we use the average, which gave better performance. And the last model is just to fine-tune end-to-end. This is the usual thing people do. And the first thing we check is what is the effect of out-of-vocabulary on the NER performance. As you can see, there's a very clear correlation between if there's a lot of similarity between the entities in the training data set and the test data set. For example, in Hausa, we can have high inter-agreement score. Sorry, not inter-agreement score. We can have high F1 score for Hausa just because the entities are similar. And for Amharic, the entities are very different. So you have lower like F1 score. And there's this nice correlation within that. And I think this is already known in the literature, which we observe with the CNN by LSTM CRF model. So the performance of the BERT-based language models actually depends on if this language if this language is supported by the multilingual BERT or the XLM beta. If it's not supported, sometimes we find CNN by LSTM CRF model to perform better, especially when you extract like embeddings from them. Of course, if you fine-tune end-to-end, transfer learning helps and you can do better. So we try to check this critically. For example, if you consider the name-based recognition performance for the supported languages in XLMR. So XLMR support quite a few African languages, at least 6 or 7. And we have like 4 of those languages in our data set. And you can see that we can do much better if we extract like sentence embedding from XLMR and we pass it through the by LSTM model. even without adding CRF, we could do better than the CNN by LSTM. A CRF model that was initialized randomly. But when you consider the NER performance for the languages that were not supported, then you see a different trend. So basically, you find out that the CNN by LSTM CRF model performs better in all the languages, I think except Rwanda. So you can see that, that because the languages were not supported, the performance was not that good. But if we, of course, if we fine tune end-to-end, then you can see the benefits of transfer learning by fine tuning end-to-end. So, and you find out that fine tuning end-to-end helps, and you do better than the CNN by LSTM CRF model. So, yeah. So the second, okay. And the last thing is that we compared multilingual BERT and XLMR. As you can see, it's very difficult to judge. But one thing that is obvious is that if the languages were being supported by XLMR, so we find that the performance is better than MBERT. But for some languages, like Yoruba, that was not supported by XLMR, but was in multilingual BERT was better. And also for Wolof, yeah, for example. So, so the second part is that we try to how to improve over the baseline models. So we tried a few approaches. Number one, to use gazetteers as additional features. So which, as we show in the literature, prior work, that this helps, even low resource languages. And also we tried transfer learning using cross-domain adaptation and cross-lingual adaptation. For example, from English to Rwanda or to Yoruba. And the last thing we tried is to aggregate all the data set, because they are not that many, sorry, it's not very large. So we could combine them and train all the training data set together to see if it's improved on individual languages. And we also aggregated by regions. Since our data set is mostly split between East Africa and West Africa, and we see if languages spoken in the same region, if it helps. So if we consider the gazetteers, so it's just like any list of entities. It could be from geonames or from a list of locations. But we make use of list of entities from Wikipedia. So this work was, actually we used the same model by Shruti and others. And the idea is that, for example, they propose using binary gazette, which is just if the entity is found in Wikipedia for that language. And if the left-hand side of the model, of the diagram, is just the normal way you would train your CNN by LSTM CRF model, where you get the character representation, you concatenate it with the word embeddings, and you send it to the by LSTM model. And as an additional layer, you have the linear layer or a CRF layer. So what we had is now Gazette features from Wikipedia, and there's another autoencoder that tries to reconstruct the Gazette features from the by LSTM. So it actually made the representation learned by the by LSTM to be richer, so it can identify more named entities. And what we find out that actually it helps for some languages, and especially if the size of entities extracted from Wikipedia is a lot. So they benefit a lot from that. For example, Nigerian Pidgin, which is PCM, actually have like five points, and also Swahili like 3 points. And just because, for example, for the PCM is an English Crow, so we use English entities extracted from Wikipedia, which helped. And for Swahili, we also have larger Wikipedia compared to the rest of the African languages, and it gives better results. And for some languages like Rwanda and I think Yoruba, we are also able to do better using this method. So apart from that, we try transfer learning, zero-shot transfer. We tried cross-domain transfer where we train on WikiANN. Basically, we are training on Wikipedia domain, and we want to test on news domain in the same language. And the second part is we train on the source language, whether English, and we want to test on an African language. So we tried different source language like English, Colonel 2003 data set. We also tried, which is a very large data set, like 10,000, over 10,000 sentences. And we compare it to Nigerian Pidgin that we annotated, which is like 2,000 sentences in the training, and Swahili and Hausa. And what we find out is that, well, when we use WikiANN, the first thing is that data set is very small. Apart from Swahili, it's around 100 sentences. So we are not able to gain a lot when we did the zero-shot transfer. But for the cross-lingual transfer, if we train on English Colonel, we can actually have a good performance in zero-shot setting, close to 40%, which is quite impressive that the entities have been learned. And this is coming from some of the language characteristics we talked about, that some of the entities have been preserved, despite that the language form is different. And but one interesting thing we find out that PCM, which is an English crow, actually performs better than for most of the languages than the English, although it's a smaller data set, like 2,000 sentences. And we even have better performance using Swahili as a source language and using Hausa as a source language. So that means that if you use a language that is closer to where these languages are spoken for the NER task, it actually helps a lot. Yeah. So when we did some analysis by averaging across Igbo, Rwanda, Luganda, Luo, Wolof, and Yoruba, we found that on average, Hausa was better than the others. And when we did more analysis, we found out that the major benefit is coming from the organization. So for example, in the English Colonel dataset, doing a zero-shot transfer, we are not able to identify so many organizations. But with the PCM, we even close to double the performance. And Swahili and Hausa even did much better than that. After organization, I think followed by location, where we benefited the most from languages spoken in that region. So we asked a question, if you have a smaller data set, for example, like Luo, pre-training on a source language like English and fine-tuning on the entire small data set, if this helps, instead of just doing zero-shot. And you can see that actually the performance is very similar, even for Wolof with less entities, although there's a small improvement if we transfer using Swahili, first training on Swahili and continue training on Wolof, we can improve the performance a bit. But on average, actually, we cannot see so much improvements across many languages. And the last thing we tried was to aggregate by regions. And if you just aggregate the data set for the West African region, Hausa, Igbo, Nigerian Pidgin, Wolof, and Yoruba, aggregate your training data set and evaluate the model on each of the test sets. And what we found out that there's some improvement over the baseline. For example, for Yoruba and maybe for Wolof, but not so much for the others. And for the East African languages, we are able to improve a bit for Rwanda, but not so much for the others. And for Swahili, it did not even improve. Yeah. So the last thing we tried was just to aggregate all the languages we have, except for Swahili. And almost in all the languages, there's an improvement. Again, except for Swahili. I don't know what's, the Swahili actually was more difficult to improve over. Yes. In conclusion, we developed the NER dataset for 10 African languages. And we also evaluate on multiple state-of-the-art models and establish some baselines that other people can, can benchmark on. So we investigate how to improve over the baseline model using gazetteers, cross-domain and cross-lingual transfer learning approaches. And in future, we plan to expand this to more languages, at least 10 more African languages through the help and collaboration of Masakhane. Thank you. So this is my first talk actually on image recognition. So I can take questions now on this before going into my own research, or yeah, whichever you prefer.
I have a question to start with. So some of the languages have a lot of morphology, and some of them have case marking. So like Kinyarwanda, I think, has the most morphology out of the languages that you worked on.
Yeah.
And then Amharic has case marking, which means that there could be suffixes on the noun depending on whether they're subject or object that could, disguise the named entity. So I'm just wondering if you used any subword units like BPE or morphological analysis.
We didn't do morphological analysis, but using the bet-based models, we actually use subword units for the training. Yeah.
But oddly, can you go back to the slide on out of vocabulary? It was near the beginning.
Yeah. Yes, this one.
Okay, so what gives something a lot of out of vocabulary is the size of the corpus or the amount of morphology or both?
It's just the number of entities that are missing in the test set.
Yeah, I guess what I'm wondering about is why does so also when we worked with the DARPA data set, I think Amharic didn't have very consistent spelling. Like they had like hundreds of ways to spell Ethiopia. So I wonder if that contributes to it being high out of vocabulary. And then Kinyarwanda has a lot of morphology. But just as a comment, what we did with Amharic is we used converted graphemes to phonemes so that we could match all the different ways of spelling Ethiopia.
Okay.
And yeah, because even name of their country, they spell it a lot of different ways. So that was interesting.
Okay.
Other questions?
Yeah, but thanks for pointing out that I will discuss more with the Amharic team. I know about some of the issues because they also complain about the data set a bit, but this was the available data set we could use for this. Yeah.
I think one other thing to comment, Lori, since you mentioned the Lorelei data, is I believe that data was from like multiple news sources and also maybe from social media. So if this is all from a single news source, it might be that they have like standardized within that news source. But like David, I think that might be one thing that you would like to think about when you want to apply this model outside of the training data, potentially, because if the orthography isn't standardized for some of these languages, the accuracy might actually drop when you apply it to like other data sources where the entities are spelled differently. But I think you know, there are methods that you could use to fix that, you know, better word encoding methods or things like that that are interesting changes. But,
yeah. Thank you for the feedback. I think we should pay attention to this. I know for Yoruba, because I've worked on this a bit more, we always standardize before. If not, we also have the same problem with the diacritics not properly placed. Yeah.
Okay, any other questions before we go on to the last part of the talk? Okay, go ahead with.
Oh, yes. Okay, so now we'll talk about something completely different. Talk about privacy guarantees for identifying text transformations. So this was what we did last year at our submission to interspeech. We are investigating how to handle privacy in spoken dialogue systems. For example, at the right-hand side, you have user talking to the system, and you first have to do speech to text, and you transcribe the text, send it to the spoken language understanding component, and you extract important information like slot values and intent of the speaker. You do the dialogue analysis or try to respond to this to the request, and it goes on like that. But when you consider this structure, there could be private information that will be leaked. For example, from the voice, you can detect the gender information, even like the ethnicity of the person just listening to the voice. And also, if you do the transcription, even if you have not tried to add information, for example, adding noise to the voice so that you're not able to distinguish the gender. After transcribing, you still have some information that might be leaked. For example, like credit card number, phone number, and other information. So defining what is private is actually not a very easy definition. It depends on the application. So, but for this work, we just streamlined the definition to the named entities. One of the critical things is that most of these voice interaction data are being stored by large companies. There was an article 2 years ago about Amazon listening to what people tell Alexa, and how do you prevent this kind of abuse by companies? And the other thing is that if everything is stored in a centralized location, this kind of information can be stolen by archives or malicious softwares. So the other thing is that the companies will always use the data, but maybe they could add another layer to de-identify the data before they use it to improve their the utility of their task. So we are doing what is the standard way of the old way of doing things, just the identification, adding user information, sensitive information, which you can do just by deletion of the sensitive information, or you can replace it by non-threatening surrogates. For example, you have how about Risk Cafe around noon on the 15th? And if you just delete maybe Risk Cafe noon and 15th as sensitive information, then you have something that is not very meaningful. But if you redact it, at least you know that something is missing somewhere. This is how, for example, legal documents have been redacted. So we can try to explore different ways of doing this, which we call replacement strategies. You have the original sentence like, "Hi, Mr. Miller, the Lufthansa flight from Frankfurt Airport to Rome is leaving by 6 p.m. If we consider the private information as just named entities, so just redacting, you can just like replace the sensitive information by something that doesn't carry so much information like placeholder. And you can also have like a type placeholder where you replace it by the category marker of the sensitive information. Or an alternative or something close to that is using a name placeholder, so using an actual word from the category. But you find a sentence like London to London, which is not very nice, it affects fluency. And so more A better way of doing this is just do word by word replacements. This has been done before, where you replace like Frankfurt Airport with New Boston. I'm not sure if there's a city called New Boston, so you might have something that is very different just because the full entities are not replaced. So the last approach is just to replace entity by another entity of the same type. So when you think about the utility of this text transformation techniques on 3 different tasks: name entity recognition, intent classification, and dialogue as classification. So we use like standard data set for intent classification. Webmobile is a dialogue data set that was collected like in the 90s about 2 people, like business people trying to schedule an appointment. And we annotated named entities for this data set. And when we just trained a BERT-based model, just fine-tuning. For the NER, this is token classification. And for the intent and dialogue as classification, it's just more of sentence classification. We fine-tune this BERT model end to end. And this is the result. We find out that if you use some of the approaches like readout, so we're showing this because previous papers already showed that it doesn't matter if you use readout or word by word, that for downstream tasks, it's okay. But what we found out here is that it's not actually this statement is not actually true. For example, for SNPs dataset that is on sentence classification, we find a huge drop in accuracy if we use readout or type placeholder or name placeholder. But of course, if we use full entity replacement, we can achieve something very similar to the initial accuracy when we did not replace anything. So apart from that, we try to provide some privacy guarantees for this, for the following reasons. So if you do automatic name entity recognition on your data set, you're not sure that everything will be, all the sensitive information will be accurately identified. So there's some privacy leaks for those ones you are not able to identify. So how can we formalize this and try to quantify what is the leakage by this method? So we introduce what's called probabilistic text transformation, where we try to replace based on probability P. And we try to formalize this using what's called differential privacy. It's a theoretic way of defining privacy where we assume like we have 2 databases that differs is just one element. And if you imagine like a very large database, so the kind of statistics you get on database 1 and 2 should be similar even if they only differ in one element. Imagine you want to compute the mean from database 1 or database 2. If it's a very large database and they just differ in one element, the mean should be almost the same. And you can formalize this as taking the probability of a mechanism applied to database 1 or an algorithm applied to database 1 is upper bounded by the exponential of epsilon. And epsilon here is called the privacy loss. So we want this privacy loss to be close to 0 so that we don't leak information. And data is just, we're saying that this is true with probability 1 minus data. Data is always a very small value, which is often set to 1 divided by the length of samples in your database. So if you, so in our setting, so you can just think about database 1, which is just a list of tokens in your data set. And database 2 is just you replace one of the tokens with another word like T2. So if after applying the identification algorithm onto this, we're able to get the same token T in database 1 and database 2, then we have done this text transformation. So we have a lemma where we say that if this text replacement pi, and pi is just a policy of how we select the replacement token. The replacement token, for example, you can select by what is the by the relative probability, by the relative frequency of the token in the corpus. Another approach is just to use a uniform distribution, where you just select any token at random, depending on the category of the that you want to protect the privacy for. So the first case would be that you have T1 and T2 are being replaced by T, and in that case, the probability here would just be one, and epsilon equals 0. The second case would be that you have a probability 1 minus p to keep the token, and you also have the probability p to replace the token. But also this also is affected by the choice of your token from the probability distribution. And this is how we formalize this is the algorithm where you first take a small value of r from a uniform distribution, and if it's less than p, which you fix as an hyperparameter, you replace t prime with t. And this is how we analyze it. And if you compare these plots, what we can see that the more, if you increase the value of p, then of course you have more privacy, you have a lower privacy loss. This is what we want to achieve. And what we find out that if you consider word by word replacement and read that, we find out that having a lower epsilon value actually caused a drastic drop in performance for the readout approach. And for the word by word replacement, it's more, the reduction is not that much. And this is some privacy guarantees for the approach. And so this is what we did in the paper. Apart from evaluating on 6 data sets from 3 NLP tasks, we provide some guarantees. So thank you.
Okay, thank you very, very much.